computations. Basically, all the messages will involve to marginalize a factor that has as many entries as variables in each of these nodes. So in this case, the largest node in the graph has 3 variables, and that's going to be the computational, but that's going to determine the computational cost of working with this cluster graph. The problem is that information is passed through this, is shared between the large nodes through these small nodes that only depend on one variable. So this means that all the information, when we do this message passing, all the messages are going to depend on only one variable. And this will produce some loss of the information. So once we have the cluster graph, we can do message passing in that cluster graph. This is called the loopy belief propagation. We just proceed as follows. We have one factor for each of the nodes in the cluster. So each factor is associated to a cluster in the graph, to a node. And then we construct the initial potentials just as before, multiplying the factors associated with the node. The initial potential for the node I is the product of the factors associated to that node. We initialize all the messages to be 1, and then we repeat until convergence, until the messages don't change. We select an edge and pass a message from that edge. We select the edge ij, and we pass a message which is the product of the initial potential associated to node I times all the incoming messages to node I except the message coming from node j. And at the end we compute the beliefs as before, just the product of the initial potential and times all the incoming messages. When this whole thing converges, we will have a calibrated cluster graph, and we will have that the beliefs at the nodes, they will approximate the marginals. So this shows an example of the execution of a loopy belief propagation, and we see that the approximation of the marginal changes as we run the method, and it's different from the true marginal. This shows some example of exact marginals and the approximation produced by loopy belief propagation, and it can be very accurate in this case. And that's more or less it. Just a summary of the whole thing. We have seen that inference in probabilistic graphical models requires it is basically the computation of these conditional distributions. Exact inference will require to sum an exponentially large joint distribution, and by using this variable elimination method, we can do computationally efficient operations by catching the intermediate results. The click tree will allow us to do exact inference by doing message passing. Basically, variable elimination can be interpreted as doing a message passing in a click tree. And by message passing, we can produce the same results obtained by running variable elimination many times. We just do message passing, and we can get all the marginals, and we don't have to do variable elimination for each variable if we want to get the marginals. When the tree width of the click tree is very large, we will have to use approximations because exact inference is going to be very expensive, and for that we can use a loopy belief propagation. So that's it. I think we can have time for some exercise.
Can I
yes.
just, like on the slide 20, is it typical that it's so different?
It depends on the problem. And one of the things of loopy belief propagation is that it might also fail to converge.
Then at least I know. But do I have any measure of how off I am?
How off you are?
Well, I get 0.8, and I have no idea whether I'm like, whether the true marginal is like. Yeah,
I think you don't.
Different or.
I think you don't. You could only.
I don't have any estimate.
Yeah. So I think you could. One way would be to use. So the thing is that if it is very expensive to compute the marginal, there is nothing you can compare with. You could compare with some other approximate method, and if you get very different results, you could say, okay, there is something wrong going on. Okay, yeah, so we can do an exercise seeing how we can do believe this message passing in a click tree to compute some of the marginals of a graphical model. So maybe we can get this up. So let's assume we have a graphical model which has 4 variables. Sorry?
If you need any colors.
Okay. So I have this undirected graphical model. I will have a factor for each maximal click in this graph. I have the factor 1, 2, the factor 2, 3, and the factor 2, 4. These are probability tables where each variable is binary. In this case, they can take value 0, 1, and 0, 1, 0, 1, and 0, 1. And these tables, they give me the form of these factors. So then I can fix a particular value for x4. I can say, for example, that x4 is I can say x4 is observed, and it takes a value, for example, 0. Then I can say I want to know the marginal distribution of all the other variables. So I can do this exactly by constructing a click tree for this undirected graphical model. Because I'm fixing x4 to 0, the first thing is that this factor that depends on x4 is going to be a factor phi2, which is going to be just x2, taking the values. If this is 0, 1, 0, 1, and the same in all the other tables. Yes?
I have a question about the values in the table. Does they have to sum to 1?
No, so the thing is that this can be a normalized distribution. So the factors, they don't have to sum 1. And I'm just going to sum when I'm computing the marginals, I'm going to sum out all the other variables in the unnormalized distribution. Yes, so that's why all these entries they don't sum 1. So I am fixing x4 to 1. I assume that I see the value of that variable. So the factor that depends on x4, it is reduced to consider only the cases in which x4 takes value 1, which leads to x2 taking the form of the factor depending only on x2, which takes when x4 is 0, it takes these values. So I reduced that factor, Then I have to construct a click tree for this graphical model. I can do the steps I mentioned before. Basically, I do the moralization. I don't have to do the moralization in this case because it is an undirected model. I have to eliminate any cycle larger than 4. There are no cycles in this case, so I don't have to do that. And then I find the maximal trees in this graph, and then I just construct a click tree for that using those maximal clicks. So the clicks in this case are given by x1, x2. It is a maximal click. X2, x3, and then x2, x4. These are going to be the nodes in my click tree. So I'm going to have a one node, x1, with the variables x1 and x2, and a node with the variables x2, x3, and then another node with the variables x2 and x4. I have these nodes, then I compute all the edges among these nodes. I assign them a weight to all these edges, which is going to be depend on the size of the subset. In this case, the subset is x2. In this case, it is x2 also, and in this case, it is also x2. So I have to find then a maximum spanning tree given this graph, and basically all the edges have the same weight. So it is enough to get a tree. And I can, for example, eliminate this edge. I consider just the tree given by these two edges, and that's fine. So now we start doing message passing. I want to pick a random node as the root. For example, this one. I will send messages from the leaves to that node. I will start by sending a message from node 1 to node 3, which is going to be just sorry, I have to assign a potential to each node. So in this case, to satisfy the family preservation property, one of the factors in the initial distribution has to be assigned to each node. So in this case, I will have the factor phi1, 2, the factor, in this case it is phi2, because I eliminated, I reduced that factor. And in this case, I have the factor phi2, 3. So then the message from this node to this other node is going to be the factor, and then marginalized out with respect to all the factor times the incoming messages to this node. There are no incoming messages. So I just marginalize out this factor with respect to the variables that are not in the subset. So I marginalize out with respect to x1. So this message is just going to be a function of x2, which takes these values. This is obtained from this factor phi1, 2, and I sum out variable 1. So I just sum these two rows. I get this message. Then I send a message from node 2 to node 3, which is done in the same way. I multiply, the message is going to be the factor, the potential associated to the node, times the incoming messages. There are no messages, and I sum out the variables that are not in the subset, which is x3. So this message is, I go to this factor to 3, and I sum out variable 3, so it takes value 1, 1, 1, 1. Okay, so now I have in the root all the incoming messages, And what I do is send the messages from the root to the leaves. So I will send a message from node 3 to node 1. And this message is going to be it's going to be the product of the potential associated to the node, this factor, times the incoming messages. So it is just the incoming messages that are not sent from this connection. So this is going to be V2 times the message coming from the other node, 2, 3. And then I have to sum out the variables that are not in the subset, which in this case they are not variables, so I don't have to do that. So this message 2, 3 is just a 1, 1. And then I have the value of this factor, which takes value 1, 0, 0,1. And this is the variable, sorry, it is better to show it this, like this. This is x2. So this is the message sent from the root node 3 to node 1, and then I have to send a message from node 3 to node 2. In this case, it's the product of this factor, V2, times all the incoming messages to node 3, except this one, which I am going to send, so it is times the message from 1 to 3. And this is just this is the value. It is just the product of the factor and the message from 1, 3. I multiply the two and I get the message that is sent from node 3 to node 2. So now I have, for all the nodes, I have all the incoming messages, and I can compute the beliefs. The beliefs are going to be just the product of the potential associated to the node and all the incoming messages. So for node, let's start with the first node. The first node, the belief for the first node is just the potential associated to the first node, which is going to be phi 1, 2 times the incoming message, which is delta 3, 1. This is just This is the message, delta 3,1, and then we have the potential. This is delta. We have the potential, which is another table. We multiply these two tables by just multiplying the entries that agree. So this is when x2 takes value 0. So I multiply this number by all these ones, and this one is when it takes value 1. I multiply these entries by this. I get another table. So the belief is a function of two variables. If I want to compute the marginals, I have to sum the corresponding rows and columns for each variable. So from here I can get another table for x1 by summing out x2. This is going to be let's assume that we want the normalized marginals. So because the distribution was not normalized, we want the normalized marginals, and that's obtained by just summing out one variable and then normalizing the resulting table. We would obtain tables that are approximately like this. This is the belief for the first node. We can then compute the beliefs for the other nodes. It's going to be the same process. We have to multiply all the incoming messages to the node times the potential associated to that node. So for the second node, for example, we have the potential associated to that node is just phi 2, 3, and then we multiply it by the incoming message, which is message 3, 2. And this is just the potential, which is this table. Times the message. And I can normalize, sum out the variables and normalize to get the marginals. And we see that the marginals for the same variable, for x2 in this case, are the same. So for the third node, it would be similar. I think that's something everyone can do by themselves. Yeah, so that's it, how you would do message passing in this graph to compute the marginals, for example.
Are they always the same?
Yes, so in this case, the marginals are guaranteed to be the same. So basically, for each node, you will have a belief factor, and basically the marginals for those belief factors will be the same across the different nodes.
So if you do an approximate algorithm of message passing?
Sorry?
If you do an approximate algorithm such as loopy propagation?
They will be, when the method converges, the beliefs will also agree, but they won't be exact. So in this case, the beliefs, they are the same as the marginalization. Each belief is the marginalization of the joint with respect to the variables that are not included in that belief factor. But in the loopy, if you do this in a cluster graph with loops, you won't get the exact marginals. So that's it, and in general, this method can be only applied to discrete variables, to probabilistic graphical models with discrete variables, but we will see in the next lectures that there is another algorithm called the expectation propagation that can be seen as a generalization of loopy belief propagation for other continuous distributions that are in the exponential family. So the idea in these discrete models, we can apply these methods because whenever we multiply two factors, we have that the result is another factor that is a probability table. So the factors always have the same form, they are just probability tables. When we work with continuous variables, we have that this property does not hold. If we have two continuous functions and we multiply them, we have that the product might not be in the same family as the original factors. And to apply this method in continuous variables, we will have to constrain the factors to belong to some specific family of continuous distributions that are closed under the product operation, so that whenever I multiply two factors, they have the resulting factor has the same form as the initial ones. And expectation propagation is just doing this message passing, can be interpreted as doing this message passing with factors that belong to the exponential family, and the exponential family satisfies the exponential family of distributions, and the exponential family of distributions satisfies this property. And we will see this in the Thursday's lecture. Okay.
Thank you very much, Jose. I don't know. Does anyone else have any questions? No, if no, then this lecture is
Thank you.
finished. And if anyone would like to talk to